The Drake equation is a probabilistic argument used to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. The equation was written in 1961 by Frank Drake not for purposes of quantifying the number of civilizations, but intended as a way to stimulate scientific dialogue at the world's first Search for Extraterrestrial Intelligence meeting, in Green Bank, West Virginia. The equation summarizes the main concepts which scientists must contemplate when considering the question of other radio-communicative life. The Drake equation has proved controversial since several of its factors are currently unknown, and estimates of their values span a very wide range. This has led critics to label the equation a guesstimate, or even meaningless. History: in September 1959, physicists Giuseppe Cocconi and Philip Morrison published an article in the journal Nature with the provocative title Searching for Interstellar Communications. Cocconi and Morrison argued that radio telescopes had become sensitive enough to pick up transmissions that might be broadcast into space by civilizations orbiting other stars. Such messages, they suggested, might be transmitted at a wavelength of 21 centimeters. This is the wavelength of radio emission by neutral hydrogen, the most common element in the universe, and they reasoned that other intelligences might see this as a logical landmark in the radio spectrum. 7 months later, radio astronomer Frank Drake became the first person to start a systematic search for intelligent signals from the cosmos. Using the 25-meter dish of the National Radio Astronomy Observatory in Green Bank, West Virginia, Drake listened in on two nearby Sun-like stars, Epsilon Eridani and Tau Ceti. In this project, which he called Project USMA, he slowly scanned frequencies close to the 21 SEM wavelength for 6 hours per day from April to July 1960. The project was well designed, cheap, simple by today's standards, and unsuccessful. Soon thereafter, Drake hosted a Search for Extraterrestrial Intelligence meeting on detecting their radio signals. The meeting was held at the Green Bank facility in 1961. The equation that bears Drake's name arose out of his preparations for the meeting. As I planned the meeting, I realized a few days ahead of time we needed an agenda. And so I wrote down all the things you needed to know to predict how hard it's going to be to detect extraterrestrial life. And looking at them, it became pretty evident that if you multiplied all these together, you got a number, n, which is the number of detectable civilizations in our galaxy. This was aimed at the radio search, and not to search for primordial or primitive life forms. Frank Drake. The 10 attendees were conference organizer Peter Pearman, Frank Drake, Philip Morrison, businessman in radio amateur Dana Atchley, chemist Melvin Calvin, astronomer Su Shu Huang, neuroscientist John C. Lilly, inventor Barney Oliver, astronomer Carl Sagan and radio astronomer Otto Struve. These participants dubbed themselves the Order of the Dolphin, and commemorated their first meeting with a plaque at the observatory hall. The equation, the Drake equation, is where n equals the number of civilizations in our galaxy with which radio communication might be possible, and R equals the average rate of star formation in our galaxy, Fp equals the fraction of those stars that have planets, N equals the average number of planets that can potentially support life per star that has planets, Fl equals the fraction of planets that could support life that actually develop life at some point, Phi equals the fraction of planets with life that actually go on to develop intelligent life, Fc equals the fraction of civilizations that develop a technology that releases detectable signs of their existence into space, L equals the length of time for which such civilizations release detectable signals into space, usefulness. Although written as an equation, Drake's formulation is not particularly useful for computing an explicit value of the last four parameters, and are not known and are very hard to estimate, with values ranging over many orders of magnitude. Therefore, the SETI League states that the importance of the Drake equation is not in the solving, but rather in the contemplation. It may be more useful to think of it as a series of questions framed as a numbers game. The equation is quite useful for its intended application, which is to summarize all the various concepts which scientists must contemplate when considering the question of life elsewhere. and gives the question of life elsewhere a basis for scientific analysis. The Drake equation is a statement that stimulates intellectual curiosity about the universe around us, for helping us to understand that life as we know it is the end product of a natural, cosmic evolution, and for helping us realize how much we are a part of that universe. What the equation and the search for life has done is focus science on some of the other questions about life in the universe, specifically abiogenesis, the development of multicellular life and the development of intelligence itself. Within the limits of our existing technology, any practical search for distant intelligent life must necessarily be a search for some manifestation of a distant technology. After about 50 years, the Drake equation is still of seminal importance because it is a roadmap of what we need to learn in order to solve this fundamental existential question. It also formed the backbone of astrobiology as a science. Although speculation is entertained to give context, astrobiology concerns itself primarily with hypotheses that fit firmly into existing scientific theories. Some 50 years of SETI have failed to find anything, even though radio telescopes, receiver techniques, and computational abilities have improved enormously since the early 1960s, but has been discovered, at least, that our galaxy is not teeming with very powerful alien transmitters continuously broadcasting near the 21 SEM hydrogen frequency. No one could say this in 1961. Modifications, as many observers have pointed out, the Drake equation is a very simple model that does not include potentially relevant parameters, and many changes and modifications to the equation have been proposed. One line of modification, for example, attempts to account for the uncertainty inherent in many of the terms. Others note that the Drake equation ignores many concepts that might be relevant to the odds of contacting other civilizations. For example, David Brin states, the Drake equation merely speaks of the number of sites at which ETIs spontaneously arise. The equation says nothing directly about the contact cross-section between an ETIS and contemporary human society. Because it is the contact cross-section that is of interest to the SETI community, many additional factors and modifications of the Drake equation have been proposed. Colonization. It has been proposed to generalize the Drake equation to include additional effects of alien civilizations colonizing other star systems. Each original site expands with an expansion velocity v, and establishes additional sites that survive for a lifetime L. The result is a more complex set of three equations. Reappearance factor. The Drake equation may furthermore be multiplied by how many times an intelligent civilization may occur on planets where it has happened once. Even if an intelligent civilization reaches the end of its lifetime after, for example, 10,000 years, life may still prevail on the planet for billions of years, permitting the next civilization to evolve. Thus, several civilizations may come and go during the lifespan of one and the same planet. Thus, if NR is the average number of times a new civilization reappears on the same planet where a previous civilization once has appeared and ended, then the total number of civilizations on such a planet would be, which is the actual reappearance factor added to the equation. The factor depends on what generally is the cause of civilization extinction. If it is generally by temporary uninhabitability, for example a nuclear winter, then NR may be relatively high. On the other hand, if it is generally by permanent uninhabitability, such as stellar evolution, then NR may be almost zero. In the case of total life extinction, a similar factor may be applicable for far, that is, how many times life may appear on a planet where it has appeared once. METI factor. Alexander Zaitsев said that to be in a communicative phase and emit dedicated messages are not the same. For example, humans, although being in a communicative phase, are not a communicative civilization. We do not practice such activities as the purposeful and regular transmission of interstellar messages. For this reason, he suggested introducing the METI factor to the classical Drake equation. He defined the factor as the fraction of communicative civilizations with clear and non-paranoid planetary consciousness, or alternatively expressed, the fraction of communicative civilizations that actually engage in deliberate interstellar transmission. The METI factor is somewhat misleading since active, Purposeful transmission of messages by a civilization is not required for them to receive a broadcast sent by another that is seeking first contact. It is merely required they have capable and compatible receiver systems operational. However, this is a variable humans cannot accurately estimate. Biogenic gases. Astronomer Sarah Seeger proposes a revised equation that focuses on the search for planets with biosignature gases, gases produced by living organisms that can accumulate in a planet atmosphere to levels that can be detected with remote space telescopes. Estimates. Original estimates. There is considerable disagreement on the values of these parameters, but the educated guesses used by Drake and his colleagues in 1961 were R equals 1/year, FP equals 0.2-0.5, Ni equals 1 to 5, fluid equals 1, Phi equals 1, FC equals 0.1 to 0.2 liters equals 1,000-100 million years. Inserting the above minimum numbers into the equation gives a minimum n of 20. Inserting the maximum numbers gives a maximum of 50 million. Drake states that given the uncertainties, the original meeting concluded that Na per ml, and there were probably between 1,000 and 100 million civilizations in the Milky Way galaxy. Range of values. As many skeptics have pointed out, the Drake equation can give a very wide range of values, depending on the assumptions. One of the few points of agreement is that the presence of humanity means the probability of intelligence arising is greater than nil. Beyond this, however, the values one may attribute to each factor in this equation tell more about a person's beliefs than about scientific facts. Using lowest values in the above estimates, R equals 7/year, FP equals 0.4, Ni FL equals 10/11, Phi equals 10/9, FC equals 0.1, and L equals 304 years, result in N equals 7 0.4 10-11 10-9 0.1 304 equals 8x 10 to 20. On the other hand, with larger values for each of the parameters above, n may be greater than 1. Using the highest values in that have been proposed for each of the parameters, R equals 7/year, FP equals 1, Ni equals 0.2, FL equals 0.13, Phi equals 1, FC equals 0.2, Drake, above, and L equals 109 years, result in N equals 7 1 0.2 0.13 1 0.2 109 equals 36.4 million. This has provided popular motivation and some funding for the SETI research. Monte Carlo simulations of estimates of the Drake equation factors based on a stellar and planetary model of the Milky Way have resulted in the number of civilizations varying by a factor of 100. Current estimates. This section discusses and attempts to list the best current estimates for the parameters of the Drake equation. R equals the rate of star creation in our galaxy. Latest calculations from NASA and the European Space Agency indicate that the current rate of star formation in our galaxy is about 7 per year. FP equals the fraction of those stars that have planets. Recent analysis of microlensing surveys has found that FP may approach 1, that is, stars are orbited by planets as a rule, rather than the exception. And that there are one or more bound planets per Milky Way star. Ni equals the average number of planets that can potentially support life per star that has planets. In November 2013, astronomers reported, based on Kepler space mission data, that there could be as many as 40 billion Earth-sized planets orbiting in the habitable zones of Sun-like stars and red dwarf stars within the Milky Way galaxy. 11 billion of these estimated planets may be orbiting Sun-like stars. Since there are about 100 billion stars in the galaxy, this implies FP is roughly 0.4. The nearest planet in the habitable zone may be as little as 12 light-years away, according to the scientists. Even if planets are in the habitable zone, however, the number of planets with the right proportion of elements is difficult to estimate. Brad Gibson, Yesh Fenner, and Charlie Lineweaver determined that about 10% of star systems in the Milky Way galaxy are hospitable to life, by having heavy elements, being far from supernovae and being stable for a sufficient time. Also, the rare Earth hypothesis, which posits that conditions for intelligent life are quite rare, has advanced a set of arguments based on the Drake equation that the number of planets or satellites that could support life is small, and quite possibly limited to Earth alone. In this case, the estimate of Ni would be almost infinitesimally small. The discovery of numerous gas giants in close orbit with their stars has introduced doubt that life-supporting planets commonly survive the formation of their stellar systems. In addition, most stars in our galaxy are red dwarfs, which flare violently, mostly in X-rays, a property not conducive to life as we know it. Simulations also suggest that these bursts erode planetary atmosphere. On the other hand, the variety of star systems that might have habitable zones is not just limited to solar-type stars and Earth-sized planets. It is now estimated that even tidally locked planets close to red dwarfs might have habitable zones. The possibility of life on moons of gas giants adds further uncertainty to this figure. FL equals the fraction of the above that actually go on to develop life. Geological evidence from the Earth suggests that FL may be high. Life on Earth appears to have begun around the same time as favorable conditions arose, suggesting that abiogenesis may be relatively common once conditions are right. However, this evidence only looks at the Earth, and contains anthropic bias, as the planet of study was not chosen randomly, but by the living organisms that already inhabit it. From a classical hypothesis testing standpoint, there are 0 degrees of freedom, permitting no valid estimates to be made. If life were to be found on Mars that developed independently from life on Earth, it would imply a value for FL close to 1. While this would improve the degrees of freedom from 0 to 1, there would remain a great deal of uncertainty on any estimate due to the small sample size, and the chance they are not really independent. Countering this argument is that there is no evidence for abiogenesis occurring more than once on the Earth. That is, all terrestrial life stems from a common origin. If abiogenesis were more common, it would be speculated to have occurred more than once on the Earth. Scientists have searched for this by looking for bacteria that are unrelated to other life on Earth, but none have been found yet. It is also possible that life arose more than once, but that other branches were outcompeted, or died in mass extinctions, or were lost in other ways. Biochemists Francis Crick and Leslie Orgel laid special emphasis on this uncertainty. At the moment we have no means at all of knowing whether we are likely to be alone in the galaxy, or whether the galaxy may be pullulating with life of many different forms. As an alternative to abiogenesis on Earth, he proposed the hypothesis of directed panspermia, which states that Earth life began with microorganisms sent here deliberately by a technological society on another planet, by means of a special long-range unmanned spaceship. In 2002, using a statistical argument based on the length of time life took to evolve on Earth, Charles H. Lineweaver and Tamara M. Davis estimated FL as greater than 0.13 on planets that have existed for at least 1 billion years. Phi equals the fraction of the above that develops intelligent life. This value remains particularly controversial. Those who favor a low value, such as the biologist Ernst Mayr, point out that of the billions of species that have existed on Earth, only one has become intelligent, and from this, infer a tiny value for Phi. Those who favor higher values note the generally increasing complexity of life and conclude that the eventual appearance of intelligence might be imperative, implying an Phi approaching 1. Skeptics point out that the large spread of values in this factor and others make all estimates unreliable. In addition, while it appears that life developed soon after the formation of Earth, the Cambrian explosion, in which a large variety of multicellular life forms came into being, occurred a considerable amount of time after the formation of Earth, which suggests the possibility that special conditions were necessary. Some scenarios such as the snowball Earth or research into the extinction events have raised the possibility that life on Earth is relatively fragile. Research on any past life on Mars is relevant, since a discovery that life did form on Mars but ceased to exist would affect estimates of these factors. This model also has a large anthropic bias, and there are still 0 degrees of freedom. Note that the capacity and willingness to participate in extraterrestrial communication has come relatively recently, with the Earth having only an estimated 100,000-year history of intelligent human life, and less than a century of technological ability. Estimates of phi have been affected by discoveries that the Solar System's orbit is circular in the galaxy, at such a distance that it remains out of the spiral arms for tens of millions of years. Also, Earth's large moon may aid the evolution of life by stabilizing the planet's axis of rotation. Fc equals the fraction of the above that release detectable signs of their existence into space. For deliberate communication, the one example we have does not do much explicit communication, though there are some efforts covering only a tiny fraction of the stars that might look for our presence. There is considerable speculation why an extraterrestrial civilization might exist but choose not to communicate. However, deliberate communication is not required, and calculations indicate that current or near-future Earth-level technology might well be detectable to civilizations not too much more advanced than our own. By this standard, the Earth is a communicating civilization. L equals the expected lifetime of such a civilization for the period that it can communicate across interstellar space. Michael Schimmer estimated L as 420 years, based on the duration of 60 historical earthly civilizations. Using 28 civilizations more recent than the Roman Empire, he calculates a figure of 304 years for modern civilizations. It could also be argued from Michael Schimmer's results that the fall of most of these civilizations was followed by later civilizations that carried on the technologies, so it is doubtful that they're separate civilizations in the context of the Drake equation. In the expanded version, including reappearance number, this lack of specificity in defining single civilizations does not matter for the end result, since such a civilization turnover could be described as an increase in the reappearance number rather than increase in L, stating that a civilization reappears in the form of the succeeding cultures. Furthermore, since none could communicate over interstellar space, the method of comparing with historical civilizations could be regarded as invalid. David Grinspoon has argued that once a civilization has developed enough, it might overcome all threats to its survival. It will then last for an indefinite period of time, making the value for L potentially billions of years. If this is the case, then he proposes that the Milky Way galaxy may have been steadily accumulating advanced civilizations since it formed. He proposes that the last factor L be replaced with FICT, where FIC is the fraction of communicating civilizations become immortal, and T representing the length of time during which this process has been going on. This has the advantage that T would be a relatively easy to discover number, as it would simply be some fraction of the age of the universe. It has also been hypothesized that once a civilization has learned of a more advanced one, its longevity could increase because it can learn from the experiences of the other. The astronomer Carl Sagan speculated that all of the terms, except for the lifetime of a civilization, are relatively high in the determining factor in whether there are large or small numbers of civilizations in the universe is the civilization lifetime, or in other words, the ability of technological civilizations to avoid self-destruction. In Sagan's case, the Drake equation was a strong motivating factor for his interest in environmental issues and his efforts to warn against the dangers of nuclear warfare. Inserting these current estimates into the original equation, using a value of 0.1 wherever the text says someone has proposed an unspecified low value, results in the range of n being from a low of 2 to a high of 280 million. As study of the concepts has gone forth, the range has increased at both the minimum and maximum ends. Criticism of the Drake equation follows mostly from the observation that several terms in the equation are largely or entirely based on conjecture. Star formation rates are on solid ground, and the incidence of planets has a sound theoretical and observational basis, but as we move from the left to right in the equation, estimating each succeeding factor becomes ever more speculative. The uncertainties revolve around our understanding of the evolution of life, intelligence, and civilization, not physics. No statistical estimates are possible for some of the parameters, where only one example is known. The net result is that the equation cannot be used to draw firm conclusions of any kind, and the resulting margin of error is huge, far beyond what some consider acceptable or meaningful. As Michael Crichton, a science fiction author, stated in a 2003 lecture at Caltech. The problem, of course, is that none of the terms can be known, and most cannot even be estimated. the only way to work the equation is to fill in with guesses. As a result, the Drake equation can have any value from billions and billions to zero. An expression that can mean anything, means nothing. Speaking precisely, the Drake equation is literally meaningless. One reply to such criticisms is that even though the Drake equation currently involves speculation about unmeasured parameters, it was intended as a way to stimulate dialogue on these topics. Then the focus becomes how to proceed experimentally. Indeed, Drake originally formulated the equation merely as an agenda for discussion at the Green Bank Conference. Fermi Paradox. The pessimist's most telling argument in the SETI debate stems not from theory or conjecture but from an actual observation, the lack of extraterrestrial contact. A civilization lasting for tens of millions of years would have plenty of time to travel anywhere in the galaxy, even at the slow speeds foreseeable with our own kind of technology. Furthermore, no confirmed signs of intelligence elsewhere have been spotted either in our galaxy or the more than 80 billion other galaxies of the observable universe. According to this line of thinking, the tendency to fill up all available territory seems to be a universal trait of living things, so the Earth should have already been colonized, or at least visited, but no evidence of this exists. Hence Fermi's question, where is everybody? A large number of explanations have been proposed to explain this lack of contact, far too many to list here. But in terms of the Drake equation, the explanations can be divided into three classes. Few intelligent civilizations ever arise. This is an argument that at least one of the first few terms has a low value. The most common suspect is, but explanations such as the rare earth hypothesis argue that is the small term. Intelligent civilizations exist, but we see no evidence, meaning is small. Typical arguments include that civilizations are too far apart, it is too expensive to spread throughout the galaxy, civilizations broadcast signals for only a brief period of time, it is dangerous to communicate, and many others. The lifetime of intelligent civilizations is short, meaning the value of is small. Drake suggested that a large number of extraterrestrial civilizations would form, and he further speculated that the lack of evidence of such civilizations may be because technological civilizations tend to disappear rather quickly. Typical explanations include it is the nature of intelligent life to destroy itself, it is the nature of intelligent life to destroy others, they tend to experience a technological singularity, and others. These lines of reasoning led to the Great Filter hypothesis, which states that since there are no observed extraterrestrial civilizations, despite the vast number of stars, then some step in the process must be acting as a filter to reduce the final value. According to this view, either it is very hard for intelligent life to arise, or the lifetime of such civilizations, or the period of time they reveal their existence, must be relatively short. In fiction and popular culture, Frederick Pohl's Hugo Award-winning Fermi and Frost cites a paradox as evidence for the short lifetime of technical civilizations, that is, the possibility that once a civilization develops the power to destroy itself, it does. Optimistic results of the equation along with unobserved extraterrestrials also serves as backdrop for humorous suggestions such as Terry Bisson's classic short story They're Made Out of Meat, that there are many extraterrestrial civilizations but that they are deliberately ignoring humanity. In The Melancholy of Haruhi Suzumiya, the Drake equation is briefly flashed during the opening theme song, a reference to Haruhi's intention to find aliens among other things. The equation was cited by Gene Roddenberry as supporting the multiplicity of inhabited planets shown in Star Trek, the television show he created. However, Roddenberry did not have the equation with him, and he was forced to invent it for his original proposal. The invented equation created by Roddenberry is. Drake has gently pointed out, however, that a number raised to the first power is merely the number itself. A poster with both versions of the equation was seen in the Star Trek Voyager episode Future's End. The equation is also cited in Michael Crichton's Sphere. In James A. Michael's novel Space, several of the characters gather to discuss the equation and ponder its implications. In the evolution-based game Spore, after eventually coming into contact with living beings on other planets, a picture is shown, along with the comment, Drake's equation was right. A living alien race. George Alec Effinger's short story One uses an expedition confident in the Drake equation as a backdrop to explore the psychological implications of alone humanity. Alistair Reynolds' Revelation Space trilogy and short stories focus very much on the Drake equation and the Fermi Paradox, using genocidal self-replicating machines as a great filter. Stephen Baxter's Manifold trilogy explores the Drake equation and the Fermi Paradox in three distinct perspectives. Ian MacLeod's 2001 novel New Light on the Drake equation concerns a man who is obsessed by the Drake equation. The Ultimate Marvel comic book miniseries Ultimate Secret has Reed Richards examining the Drake equation and considering the Fermi Paradox. He believes that advanced civilizations destroy themselves. In the story, it turns out that they are also destroyed by Galactus. Eleanor Ann Arroway paraphrases the Drake equation several times in the film Contact, using the magnitude of NA and its implications on the output value to justify the SETI program. The band Carbon-Based Lifeforms mention the Drake equation in their song Abiogenesis and their 2006 album World of Sleepers. The Drake equation has also been cited by Bill Bryson in his book titled A Short History of Nearly Everything. Mentioned by a character in George's Cosmic Treasure Hunt by Lucy and Stephen Hawking. Mentioned in episode 602 The Truth Is Out There of the BBC series New Tricks. Mentioned in Jupiter War, the third book of the Owner trilogy by Neil Asher, as a problem the owner would investigate in the future. The July 2013 issue of Popular Science, as a sidebar to an article about the Daleks of Doctor Who, includes an adaptation of the Drake equation, modified to include an additional factor dubbed the Dalek variable, rendering the equation thus. The added variable at the end is defined as the fraction of those civilizations that can survive an alien attack. See also, astrobiology, Goldilocks principle, Kardashev scale, planetary habitability, rare earth hypothesis, ufology, references. External links, Interactive Drake equation calculator, Rood, Robert T. James Eschville. Are We Alone? The Possibility of Extraterrestrial Civilizations. New York, Scribner. ISBN 0684178427. Bates, Gary. Alien Intrusion. Master Books. ISBN A0-89051-435-6. Morton, Oliver. A Mirror in the Sky. In Graham Formelo. It Must Be Beautiful. Granta Books. ISBN A1-86207-555-7. Only a Matter of Time, says Frank Drake. A Q&A with Frank Drake in February 2010. Frank Drake. The ET Equation, Recalculated. Wired, Macromedia flash page allowing the user to modify Drake's values from PBS Nova. The Drake Equation Astronomy Cast episode number 23, includes full transcript. The Drake Equation, a critical examination of the Drake Equation. The Drake Equation animated simulation of the Drake Equation, the Alien Equation September 22, 2010, BBC radio program Discovery.